class. Let me put on this presentation mode. So up until now, in the previous class, we have looked into the octahedral field, what happens when the ligands approach in an octahedral symmetry. Six of the ligands approached, and they approach along the axis, as a result of which we found that the orbitals, those which are directly along the axis, that is the dx squared minus y squared, dz squared, it goes up high in the energy level, whereas the dxy, dxz, or dyz, which are in between the axis, they are the ones that are lowered in energy. So, because they are not directly electron-electron repulsion between the ligand and the d orbital electrons in the dxy, dxz, and dyz is not much there, as a result of which they become lowered in energy. So you have, that was the splitting that we saw in octahedral field. Then we looked into uh, the tetrahedral field. In a tetrahedral, we saw what happened in a tetrahedral field, where the electrons, the ligands were approaching in between the axis, this structure of a tetrahedron. We said that imagine it as a cube in which the ligands are approaching, two diagonally in the front face and at the lower side, two in the oppositely diagonal sides. And they are approaching in between the axis, as a result of which those orbitals which are lying in between the axis, they get increase in energy. So dxy, dyz, dxz became higher in energy, and the dx squared minus y squared and dz squared becomes lower in energy. And since there are only four ligands that are approaching, as compared to the octahedral field, where you had six of them approaching, this energy difference, this lowering of energy and increase this delta T, is almost 4/9 of delta O. This was for a tetrahedral field. And then we looked into the square planar complexes. Square planar complexes, we imagined that they are very much like an octahedral splitting, wherein the ligands along the z-axis have been removed out. If the ligands along the z-axis have been removed out, that means what is happening? The orbitals, if along the z-axis, if it goes away, so those whichever orbitals which have the Z component in them, they become lower in energy, because no more is there any repulsion between this and the ligand that was present earlier in an octahedral field along the Z axis. So the Z orbital, Z squared, becomes lowered in energy. And not only just the Z squared, but also those, because they are not facing it. The Z has totally gone off the ligands, which was there in this axis in an octahedral field. Now that Z is not there, so this also becomes lowered in energy. So all those having the Z component in them, they become lower in energy. And while, since the ligands are still present along the X and Y axis, so you have the XY becoming higher in energy, X squared minus Y squared becoming higher energy. So we saw the splitting that take place, the crystal field stabilization energy in a octahedral field, in a tetrahedral field, and in a square planar complex. Okay, and today we'll look at Hahn-Taylor effect, and we'll go to the tetragonal distortion in a minute. Right now, I'm leaving it right now. Uh, I would like to tell you a little bit about the Hahn-Taylor effect. Okay, so let's take it into a slideshow. So this is Hahn, although it's written as Jean Taylor, J is there, the J is silent here, you pronounce it as her. That's why chemistry is interesting. You get to know here a number of interesting names, whether it is Hahn, Teller, you had we always pronounce de Broglie, but it was de Broglie, supposed to call him as de Broglie. Then you have very interesting terms like you write it down as Nephilogzetic effect, but you pronounce it as Nephilectic effect. You do have interesting and intriguing words in chemistry. That makes chemistry all the more interesting. Let's see what this Hunt-Teller effect tells us. First, let's read what it is. Then I'll try to explain what do we mean by this. So it says that if the ground electronic configuration of a nonlinear complex is orbitally degenerate, the complex will distort so as to remove the degeneracy and achieve a lower energy. Seems a number of complex terms coming here, but let's demystify it. Let's try to explain it in a simple way and try to understand first what is this orbitally degenerate or electronically degenerate actually means. What are we trying to explain by this, understand by this? So let us look at this. Take an example of, let us say, titanium. Okay. So titanium in a +3 oxidation state has got a single electron in the d orbital. Okay. So titanium in +3 oxidation state with a single electron. Now this single electron can stay either in, we can write this like this, either if it is on dxz, then it will be dx1, dxy0, dyz0. It can either stay in dxy, then it will be dxz0, dxy1, dyz0. Another option is that why not, since all three are equivalent in energy, dxy, dxz, dyz, that it could have been in dyz too. It can stay in dyz. So now you're seeing that this single electron of titanium has an option to stay in either this or this or this. So such a condition we call as electronically degenerate condition or orbital degeneracy. So the term is orbital degeneracy, meaning that since these orbitals are same, the energy of dxz, dyz, dxy is same. So the electron could have been in either of these. But now think of it, that if the electron is in this, but there's no electron here, no electron here. So they cannot remain, that's what the Hunt-Teller theorem tells us, that they cannot remain degenerate. Because definitely, though, if suppose it is on this axis, then definitely this is feeling the ligand that is coming. This is feeling the repulsion much more. So the ligand will try to move away, because this will not feel so much, this will not feel so much, because there's no electron in these two. But this is going to feel the repulsion because of the ligand, because there is one electron here. So we cannot say that they are equivalent energy. They cannot be. So this will become now, since the ligand, because there is repulsion between the ligand that is approaching and this orbital, the electron that is here, the single electron here. So what will happen? This degeneracy will be lost. Now these three orbitals can no more remain degenerate. What will happen? This will become lower in energy and these two will become higher in energy. So the degeneracy has to be lost. So whenever you have a nonlinear molecule where such an option exists, where you can have such a state, electronically degenerate state. Please understand, what do we mean by electronically degenerate state? Wherein, although they are equivalent, we say that they are triply degenerate, isn't it? T2G, we say that dxy, dxz, and dyz are, all three are equivalent in energy. But we understand, we know that if this contains only one electron, these have no electrons in them, then definitely this is going to face the ligand which is there, and this electron will face greater repulsion. So the ligand will move away from it. The minute it moves away from it, then this becomes lower in energy. So this will become lower and these will become higher in energy. Same thing will happen for a D2 ion system where you have two electrons. Then those two will, suppose the electron is here and here, then these two will come down, one will go up. Now let us say, because we will have, why will it be electronically degenerate? Because the electron can exist in dxz1, dxy1, dyz0, or it can be dxz0, dxy1, dyz1, or it can be dxz0, dyz0, dxy1, dxz1. So with the D2 system will also be electronically degenerate, because although there are all three are equivalent, but you are having unequal number of electrons present in them. Now let us say, what about a D3 system? D3 system meaning 3 electrons. So 1 electron here, 1 electron here, 1 electron here. Will that system be electronically degenerate? When there are 3 electrons, D3 system, you have dxz1, dxy1, dyz1. Will such a system be called electronically degenerate or not?
No, ma'am.
No, it cannot, because all three are containing one electron in them. Very good. So it is, such a system will not be electronically degenerate. It will be a non-electronically degenerate system. So it will be non-degenerate state, because there is one electron in each one of them. So this is a truly a degenerate state. Triple degeneracy is
Okay,
here.
ma'am.
Yes.
I mean, previous case you told that these are not degenerate. I mean, dxz1, dxy0, and dyz0. Ma'am, are they
Huh.
degenerate or not? I mean, like, because in text it is written such a situation is called an electronically degenerate state. But
Huh.
as it, but
No,
as it
because
is
normally,
containing,
yes, say it. Hmm.
as it is containing one electron dxz, it will face more repulsion. You told, ma'am. So it will have
Hmm.
different energy from
Yes, of
dyz.
course. So that they are, we normally, what do we say? Double case, we say that they are electronically degenerate, isn't it? So it is that they are a system where this is triply degenerate, and you have a double degeneracy in EG, and T2G we have triple degeneracy. So we say that, but here what is going to happen? The degeneracy gets lost, and it will be it is a misnomer here when we are putting it like this. For a nonlinear molecule in an electronically degenerate state, the degeneracy does not stay. Ideally, we say that they are T2G is electronically degenerate, but the degeneracy is lost here. And what do we have? We have that this becomes lower in energy, and these two systems, the system changes itself in such a way that it removes the degeneracy and lowers the energy. Okay. Whereas in a system like chromium in a +3 state, they are in this, no such thing is going to happen. No such distortion will take place, because they are already in a state where in which they are all three of them are in a degenerate state. It's wrong to say that it is electronically non-degenerate state. They are in the equivalent amount of numbers of electrons are present here. So the Hahn-Teller theorem predicts that a non-linear molecule that has an electronically degenerate state, distortion occurs so that the degeneracy is removed, and the consequence is that the symmetry of the molecule is lowered, and the system becomes more stable by losing energy. So why is it becoming more stable? Because the ligand and the electron repulsion takes place. That causes the ligand to shift a little bit away from the electrons. So it moves away. If it moves away, then this becomes lowered in energy, and others as a consequence will become higher energy. The amount of that this gets reduced, this will get increased in energy. That way, the stability of the system is improved. So they lose energy and they become stable. Now, so this is what the statement meant, that if in a ground electronic configuration of a nonlinear complex, it is electronically orbitally degenerate, the complex will distort so as to remove the degeneracy and achieve a lower energy. Now, what can happen in such a case? What will happen is that in this, you will have two types of distortion taking place, depending upon which of the which is of the two orbitals or of the three orbitals, where exactly are the electrons present. So you can have two types of this distortion. One is known as Z-in distortion. One is known as Z-out distortion. Now let us try to understand how does it happen? how can I get a Z in distortion and how can I get a Z out distortion. It is mostly, normally you can get to any of these systems. You can have it in a D1 system or a D2 system or a D4 system, D5 system, and not a D5 system, D6, 7, 8. Most prominent are the ones when you have it in the EG level. When you have electrons present in the EG level, that is a greater change is there, more distortion is there. And the most prominent one, you can see it in a D9 system. A D9 system means that you have all the electrons, dxy, dyz, dxz, 2, 2, 2, and in d squared minus y squared and dz squared. Say, let us say there are 2 electrons in dz squared. Okay, let us assume that 2 electrons are in dz squared and 1 electron is present in 2 electrons present in dz squared and 1 electron present in dx squared minus y squared. So now what is going to happen? There are 2 electrons in dz, 1 in dx squared minus y squared. Obviously, those 2 electrons are going to repel the ligands around the dz axis. So the ligands will try to move away along the dz axis, the ligands that are coming. This will move away, this will move away. This will try to move away from each other. So this moves this side, this moves this side. So what happens as it moves away? The dz squared becomes lowered in energy. So the dz squared becomes lower and dx squared minus y squared, they become higher in energy. So because of this z elongating out, if this elongates out, what is going to happen? This is a Z out phenomena. This is what we mean by a Z out phenomena, where if we have 2 electrons here and 1 electron in this, then this is going to, the ligand along the Z axis is going to feel a greater repulsion, as a result of which it is pushed out. When it moves out, it elongates. So what you call it a Z out phenomena. Now the reverse case can take place is a Z in phenomena. So a Z out phenomena, what is happening? This is moving out. If this is moving out, then the XY axis is coming closer. So you have 4 short arms and 2 long arms. So the long arms would be the Z ones. This axis and this axis will become longer for this octahedral structure. These 2 axes become longer, and the 4 axis, that is 1 arm, 2 arm, 3 arm, 4 arm, they are going to move inside. Think of an octahedral structure. This is an octahedral structure wherein this is a parallelogram, and these are the 2 axial ones, one on top, one on below. So these 2, when they are stretched out, what is happening to all these 4? They are going to squeeze in. So if they squeeze in, we call it as 4 short arms and 2 long arms. Reverse can take place when we have and this was called as Z out phenomena. Why? Because the electrons, there was unequal number of electrons. You had 2 electrons here and you had 1 electron here. The same phenomena would have occurred if it was just a single electron. If it was on the Z axis, then it would lead to a Z out phenomena, causing that one to lower and these 2 electrons, the Z axis stretching out, causing 4 short and 2 long arms. Now, if the reverse takes place, wherein there are 2 electrons in dx squared minus y squared and a single electron in dz squared, what happens in that case? Since there are 2 electrons in dx squared minus y squared, these are the ones that are going to be repelled outward. So they move outward. They get stretched out along this parallelogram. So the 4 arms, the 4 sides of it, they get stretched out. So if they get stretched out, what happens? These 2 will be squeezed in. So these 2, the Z ones get squeezed inwards, and the XY axis orbitals get, arms get stretched out. So that is a Z in phenomena. So this is an example of a Z in phenomena, wherein the ligands along the Z axis are squeezed inwards, and the ligands along the XY axis are stretched outwards. Whereas this is a Z out phenomena, wherein the ligands along the z-axis are stretched out, and as a result of which the ligands along the xy axis are squeezed in. So you have 4 short arms, 2 long arms here. In this, we have 2 short arms and 4 long arms. So depending upon wherever the unequal distribution of electron is, whether it is on the xy axis or on the z axis, you can get a z in and z out phenomena. Have I made this clear? Any doubts in this? Try to imagine this parallelogram and this axial points there. So when they stretch out, so it can be any such system which are having such a system either in a D1 or a D2, not in a D3, not in a D5. But most pronounced, you find it in a D9 system where you have electronic distribution, wherein you have all dxy, dxz, dyz filled up, and dx squared minus y squared having 1 electron. And such a system you will see a z out phenomena you will see when you have 2 electrons in the dz squared. Z in phenomena we'll see when we have 2 electrons in the dx squared minus y squared. Okay. Any doubts in that? Do you understand this Hahn-Teller theorem? This is all that it is trying to tell you. So let's read it. Maybe now it will become clearer to you. Okay. Consider there are 2 types. We said the consequence of this is that 4 long along xy axis and 1 short bonds. This is known as, no, where was I reading it? We'll consider 2 types of distortions to be operating, Z in and Z out. In the case of octahedral complex, the tetragonal, and such distortions are termed as the tetragonal distortions. So what happens that it doesn't remain a complete octahedral structure. Distortion takes place, either elongation takes place of the Z arm or compression takes place. So we say that the octahedral structure gets tetragonally distorted. So in case of octahedral complexes, the tetragonal distortion reduces the octahedral symmetry of a complex to tetragonal structures, producing either elongated or compressed tetragonal bipyramidal structure. So what do we call them? You have, instead of a completely octahedral symmetry, what we are getting is a tetragonal bipyramidal structure. And that bipyramidal structure, in that we can either have a 2 long and 4 short, meaning Z out phenomena, and or we can have a compressed one wherein you have 4 long and 2 short, that is a Z in phenomena. So both the types of tetragonal bipyramidal distortion can take place, and that would depend upon in which of the orbitals we have the electrons residing, whether it is in the xy or it is in the z-axis. So consider a case of hexaquo titanium complex, which has got a D1 system. To remove the electronic degeneracy, the T2G orbital is split, the energy of dxz and dyz orbital are raised in energy, while in this case, dxy, if the electron is residing in the dxy orbital, then in that case, this becomes lowered in energy because along the xy plane, the ligands are going to push out. That will cause these, the ones which are along the z-axis to get increased in energy. The separation, so if you could assume it as the separation, let's say is delta 2 in the Eg set of dz squared orbital is raised in energy in comparison to the dx squared minus y squared. So that is what is happening, not only in just if it is a D1 system, then it is not just the T2G, it will be the Eg also in which you will have this distortion taking place. So in that case, you have in the Eg set, the dz squared orbital is raised in energy in comparison to the dx squared minus y squared, and the separation is delta 1. In this way, the lone electron is on the dxy orbital and the electronic degeneracy has been removed. The repulsion experienced in the orbitals containing the xy component is more than the orbitals containing the z component. The consequence of this is that we have 4 long arms along the xy axis and 1 long along the z axis. 4 long along the xy axis because the